All right, we should be live. Welcome back. This is the third session of Orion Uncovered here from Leiden. We are in the late afternoon here, so good morning to anyone in the suitable time zone. And before we start with the next talk, as listed on the website, we will actually briefly go over some introductory slides that we had this morning, if I can get that to work here. So just a second. So you should be able to see these slides now. Does that work? Okay. So just a brief reminder, this is the Scientific Organizing Committee and the Local Organizing Committee put this meeting together here in Leiden. Funding provided by the Netherlands Organization for Scientific Research, and we are hosted here by University of Leiden. And this is based on a previous workshop that we organized in Vienna in 2015, where we also tried out this method of having online talks first and then an unconference after that. So it might seem very experimental, but we have some previous experience running this, and we are collecting more experience, and we are curious about anybody's comments about this. The conference goals are that we will look at Orion as a paradigm for star formation. Lots of data is available, lots of new data is available, new simulations. So we really want to look at the state of the art, particularly what has happened in the past couple of years. It's a nice benchmark for theory versus observations, a test case for new instruments and facilities. And so we would like to bring all of this into context for Orion. The conference format is such that we will have today and tomorrow with online talks broadcast via YouTube. You can find all the links on the website. This will conclude the presentation part of this workshop, and then in the second half of the week, we'll have an unconference here in Leiden for 3 days with discussion topics. On the website, which is again listed here, you can find general information, the program for the first part in particular, all the abstracts, links to the YouTube streams, and also the recorded talks. If you missed the session, you can actually click on the same link and just watch the previous presentations. How to participate and how to interact during the online talks. We will collect questions using the YouTube live chat window. That's usually on the right-hand side of the video feed in the YouTube window. You will probably already find some other comments there. We will read out questions to the speaker after the talk. We will not interrupt the talks, but then afterwards we can go over any questions. We will also have some local questions, most likely here from the audience in Leiden. And then after the talks, if there are any follow-up discussions, since we will only have this chat window during the presentation and during the sessions, we also have the Google group as explained on the website. A quick look at the program. So we are about to start the first afternoon session of the first conference day, and we'll get started right after this. All right. So I will try to switch over to the first speaker of the afternoon, Tom McGath. Hi, Tom.
Hi, can you? We won't want to do that. Let me do some reverb effect. Hello?
Yeah, like this, it seems fine.
Okay. It would help if I unmute.
Yeah.
Okay, well, let me see if I can start the
Yeah,
present.
if you can start sharing your screen, then we can go ahead.
Oh, let me do this. Share screen. And then are people see? Why is this not working? Okay, should be showing the screen. Why is it not sharing the screen?
You need to go on sharing in screen.
Oh, do I have to click on this? Oh, I see.
Yep, there.
Share. And then if I go like that.
Yeah, all right.
Okay, excellent. All right. Well, first, I just want to thank the SOC and the organizing committee for putting this together. It's a real pleasure to talk here, to the entire world on Orion, and this is just sort of a fantastic sort of meeting and topic. So I'm really pleased to be here. The topic that I'm going to be discussing is mass accretion. And so mass accretion, we usually think of mass accretion onto a single star. We study mass accretion onto individual young stellar objects. But I'd like to sort of expand that discussion to mass accretion onto whole clusters. And so the idea is very simple. If we know the mass accretion onto individual stars, and we can measure this for all the individual stars in a cluster, then we can sort of measure the total rate at which the interstellar medium is being converted into stellar mass for the entire cluster or for an entire molecular cloud. And so we can scale that up. And this is interesting because we are interested in measuring star formation rates. And so if you have a mass accretion rate, a combined mass accretion rate for an entire cloud, then you can actually determine the star formation rate, and you can compare it to other methods for determining star formation rates. Now, this is work that is basically utilizes a large body of work developed by the Herschel Orion Protostar team, or HOPS team. And so I just wanted sort of to acknowledge their contributions, which will be done throughout this talk. I also wanted to acknowledge this great image of the HOPS data, which I actually found on Twitter as processed by Judy Schmidt. It's beautifully done. It's nice to find my own data sort of sitting on Twitter, beautifully processed. All right. So why is this interesting? Well, there's a wide body of work, or I should say a growing amount of work, which is using the number of YSOs as sort of a proxy for the star formation rate. And you'll see this in particular in recent studies that are trying to identify star-forming laws in nearby molecular clouds. And so there's the work by Gutermuth, where it basically counts the surface density of young stellar objects and correlates that to the gas density. There's further work by Lombardi and Lada et al., where they do the same thing, but using basically the density of protostars. And then more recently, there's the work by Pockrell et al., who uses both techniques. And so we're very interested because we're finding these very strong correlations between the density of objects and the surface density of a gas. And so these are interpreted as star formation laws, where the star formation rate goes as the power of the gas density. Now, to do this, we're making a very sort of simple calculation of the star formation rate, where we basically say, okay, the star formation rate is a number of dusty young stellar objects divided by the lifetime of those dusty young stellar objects. And so you can choose your favorite lifetime here, but we think that disks last around 2.5 million years. And so we could divide by 2.5 million years, and then we get a star formation rate. You can also do this finding a more recent star formation rate by using the number of protostars and dividing that by the lifetime of the protostars, where commonly a number like 500,000 years is utilized, which is that one, for example, is from Dunn et al. 2014. Now, there might be an issue with this. So here is a beautiful column density map of the Orion A cloud from Stutz and Gould, and I have overlaid the distribution of the protostars from the HOPS program, with the size dependent on the luminosity and the color dependent on evolutionary state. The red ones are the younger ones. And you can sort of see the difference in the density between the northern part of the Orion A cloud, where there's a very high density, that's the integral-shaped filament and the Orion Nebula cluster. And then as you continue downward in declination, the density of YSOs tends to get lower and lower and lower, all right? Now, the interesting thing is if you just take the luminosities from the Hops paper from Furlan et al. 2016, and you compare them as in declination, fortunately, the Orion A cloud is basically almost vertical in declination, so it makes a convenient way of dividing to different regions. You'll find that there is sort of a trend in the sense that the objects toward the southern part of the molecular cloud tend to be low luminosity, and the ones toward the northern part of the cloud in the integral shaped filament and in the Orion Nebula cluster tend to be higher luminosities. And notice that in these two plots, I'm plotting the log of the luminosity. One is just the bolometric luminosity. The other one is basically calculated by model fits. But the trend is there in both, even though the luminosities differ a bit. Right? And so this is actually also seen in another paper, Kuryakova et al. And since we don't think the IMF is changing systematically across the cloud, one interpretation of this is basically that the rate at which stars are forming, basically the rate at which protostars are being converted into, accreting their full mass and being converted into stars is increasing as you go to higher declinations. In other words, the lifetime of a protostar is decreasing as you go to higher declinations. So maybe this sort of calls us to sort of investigate different ways of calculating the star formation rate. And one other way we can use is the integrated luminosity of the protostars. We can do this for protostars where we've measured the full SCD. And from you can sort of write a simple equation as I have written here, where you just take the luminosity and you just divide out sort of, the gravitational constant, the mass to radius ratio, and sort of what you expect the average final mass of the star to be, and you get sort of a rough star formation rate. And you can play around with some of these numbers, but in the following talk, I just took the average mass from the IMF of around a half solar mass and a mass to ratio for models of protostellar evolution of about 0.1 solar mass per solar radii. That may be more constant than you might think because the deuterium burning sort of sets a roughly constant mass to radius ratio for protostars. Okay, so if you look here, I'm going to have to accelerate a little bit. On the left side, we just show an example SED from the HOPS program. And as I said, you can integrate that SED and you get the bolometric luminosity, or you can take the model fit, which is the line in blue, which corrects for inclination and extinction, and that gives you L tot, the total luminosity as predicted by the models. Now, if you actually plot that as a function of the model predicted local envelope mass, we found sort of that the luminosity, and this is the work of Fisher et al. 2017, decreases with the envelope mass, right? And we can interpret that basically that the envelope is sort of decreasing, the mass of it's decreasing exponentially with time. And so as the star initially ramps up in luminosity as the central protostar grows, but then the envelope density basically decreases, the infall rate decreases, the accretion rate decreases, and the overall luminosity of the protostar drops. And in the upper left-hand corner, I give you the formula where it's a combination of intrinsic and accretion luminosity. And so you can sort of see on one side, you're dominated by accretion. The other side, you're dominated by the intrinsic luminosity of the sources. Now, we only really want to count, I'm going to sort of skip through this momentarily so I have time to actually to my point. We're basically just going to count the objects which have bolometric temperatures below 100 Kelvin because those are the ones that are really dominated by accretion luminosity. And we're going to throw out the rest of the protostars. Right. So here we're going to start with the integral shape filament. On the left, we have the Spitzer image with all the dusty YSOs superimposed. On the right, again, we have the column density map with the distribution of HOPS protostars superimposed. We'll also see, if you look carefully, these orange dots sort of toward the center. These are objects toward the Orion Nebula where we could not obtain full SEDs for them, but we identified them as protostars in previous Spitzer data. They'll become important in a moment. All right, so the first thing we do is we just bin everything by declination because it's simple, and we can do we can look at it as different ways. We can basically bin a number of protostars. We can bin a number of protostars without HOPS data, which is the no HOPS in red, and we can bin a number of protostars with T-bol less than 100K, right? Now, the other thing we can do is we can actually just add up the total amount of protostellar luminosity within each one of those bins. And we do that for the bolometric luminosity, and then we do that also for the total luminosity. And then we can also make a correction for the sources that are not detected by HOPS. And I could go into more detail a bit later how I make this correction, but it takes into account sort of the average luminosity of the protostars where we have full SEDs. And so what you want to look at is the red histograms are sort of the total luminosity, both of the hop sources plus those that are included in the correction. You can see it's significant in this area because of the Orion Nebula. Now on the right, we can now calculate the total star formation rate using these different luminosity. Well, on the top side, we basically just use the number counts. So we take the number of protostars and divide it by the lifetime of the protostars. We take the number of YSOs and we divide it by the 2.5 million years. On the bottom two panels, we actually show the star formation rates determined using the luminosities with the equation that I showed earlier, right? And so you see that we're getting in all of them values around a few times 10 to the minus 4. If you use L tote, you get a higher value because it tends to inflate the luminosity, rightly or wrongly. If you use the YSOs, you'll find that the peak is shifted a little bit. But one thing that's actually important to note here is that the star formation rate we get from just the number counts of the protostars is much lower than what we are actually getting using other methods. Now I can expand this to the entire Orion A cloud now. And so now we're going all the way from minus 4.5 to minus 9 in declination. Again, the top is from the number counts. So we just count the number of protostars per bin and so on. And then the bottom two are where I'm adding up the luminosity. So each bin is the total luminosity within that declination bin of all the protostars added up. The red one being with an additional correction for the no hop sources. And as you can see, most of the correction for the no hop sources is toward the Orion Nebula, where again the nebulosity prevents us from determining those. Now I can convert those to star formation rates using the methods I described. And so if you use the number counts, then we get the ones on the top. Those are number counts divided by lifetimes. If we use the luminosity in the equation I gave, we get the ones on the bottom. Now the overall characteristic is very similar. You get a very high star formation rate toward the Orion Nebula cluster in the integral shaped filament, and then basically it drops as you go down to the bottom of the cloud. That's not going to surprise anyone. The one thing that's very interesting is if you look at the amplitudes, that again, towards the Orion Nebula cluster, the rate inferred simply from the number of protostars is much lower than the other measurements. And I think this might be due to the fact that the star formation, that the lifetime of protostars may be actually shorter in that particular region. In other words, the stars are actually forming much more rapidly. And so if you used a 500,000 year lifetime, you're basically going to underestimate the star formation rate, right? So that's sort of the basic point, that these methods they agree to some level, except for the one using the protostellar lifetime, but there are other differences that need to be investigated in more detail, right? And so here's just basically the summary that we shouldn't really measure the star formation rate from just one method, and we really need to now intercompare multiple methods and not depend on one. We need to really understand the discrepancies between these, because I think there's some really sort of essential both physics of low mass star formation as well as systematics for measuring the star formation rate that need to be understood before we sort of expand outward into the galaxy, for example, using JWST and such. And the other thing is that we really also need to correct for biases due to incompleteness, and that has to be an important part of any of the methods. All right, thank you.
Excellent. Yeah, thank you. Are there any questions? Okay, we have a local question here from Alvaro.
Yeah, so Tom, really nice presentation. I have a question because you said that so the star formation rate or the accretion rate grows toward the northern part of the interval filament.
Yeah, the star formation rate is much higher in the integral shaped filament.
The IMF does not change. So at some point, so you accrete faster, but you do not accrete more, right?
So there's a little bit of the very high end of the IMF has changed, but the bulk of the IMF is relatively constant. So if that stands, then basically right. It's not the higher accretion rate doesn't mean you're forming more massive stars. It just means you're forming stars faster. Yeah.
Thank you. Yeah, there's a second question here locally.
So maybe a naive question, but I don't know, is it possible that there are environmental effects, the stellar feedbacks, reducing the lifetime of the protostar?
I don't, well, you know, for other reasons, I don't think necessarily it's feedback. It's a shorter time. I think it's, if you actually look across the cloud, there's a range of densities. So the gas is simply denser toward the upper part of the cloud than the lower part of the cloud.
Yes,
and so the free fall times and time scales are much shorter than that. And so I think it's less because the filaments are actually fairly well shielded from the feedback from the nebula. Now there might be some feedback in the sense that the densities are higher in part because of the feedback. So more indirect effect.
Yeah, so you don't see differences between the different density parts?
The densities are
the discrepancy between your start measurement rate estimates?
Yeah, I think there's a correlation between there's higher both column densities and volume densities toward the northern part of the cloud, and that probably drives this difference at some level. Yeah.
All right. Any more questions? Okay, so let's thank Tom again. Next speaker is Salvatore, and I will actually switch over.
Hello, can you see me? I cannot hear you.
Salvatore, if you could share your screen, then we can put it into the screen.
Sure.
Excellent, I see something.
Okay. Okay, can you see my
Perfect.
presentation?
Yes, excellent.
Okay.
So yeah, so we'll look at some higher energies, and yeah, Salvatore, please go ahead.
Okay, so good afternoon, everybody. I'm Salvatore Colombo. I'm a PhD student from Università di Palermo and Sorbonne University in France. And today we'll discuss you about part of the results obtained during my PhD and about the effects of the intense coronal activity on the stability of disk of classical Tethys stars. So everybody knows that what is a classical Tethys stars. It's a young star surrounded by a circumstellar disk, and star and disk interact mainly through the accretion of mass. And this process is regulated by the magnetic field. In fact, the disk extends internally up to the truncation radius, and in this region, the magnetic field is it's strong enough to lift up the material and to force and to funnel it into magnetic field, into the what we call accretion column. And so the accretion column, the material hits the stellar surface and accrete onto the stars. So another things that characterize classical Tethys stars is that they are strong X-ray emitters. And there is one fundamental and debated issue in this field, and it's the apparent correlation between the coronal activity and accretion. So there are studies that suggest that the accretion onto the star modulates the X-ray emission through the absorption of the X-ray emission or through the destruction of the coronal structures. On the other hand, there are studies that suggest the opposite, so that the coronal activity can enhance the accretion onto the star. So in fact, when you have more X-ray emission from the star, you have more photoevaporation, and the material that photoevaporates from disk can accrete onto the stars. This activity in classical Tethys stars is mainly produced by flares, and that are very frequent, much more energetic than the one that we observe in the sun. Those flares were observed during a COOP campaign, a deep field observation in the Orion region. And thanks to this observation, we were able to infer the temperature of this structure and the fact that they are long-lasting. And due to the fact that they are confined by the magnetic field, and we know that the temperature and the time of this, the lifetime of this structure, we can calculate the length. And studies suggest that these flares, some of the flares observed during COOP campaign, were too long to connect to 2 points of the stars. So they have to be confined in structure that links the stars to the disk. At this point, one may ask, but is it possible that this kind of coronal activity may perturb the disk stability and may, for example, trigger accretion? So we have a partial answer to this, and it's yes. In 2011, our London collaborators developed a 3D model, 3D MHD model, that suggests that the most energetic flare observed during the COOP campaign is able to perturb the disk and to trigger accretion. And in this animation, I will try to explain you how. So here we have a star and the disk. So let's assume that a flare occurs on the disk surface. The third thing is that the hot material evaporates from the disk as it channeled in a hot loop and form this hot loop that links the star to the disk. And this is the flare that we observed during the COOP campaign, for example. But the other things that the flares produce is that is an overpressure wave that propagate and then travel through the disk. And when it reaches the other side of the disk, push out the material out of the equilibrium. And the material out of equilibrium has to accrete onto the star and forms an accretion stream. So my goal for this project was to understand if, in a more general case, so we are not exploring, with London collaborators explored the most energetic flares, so the extreme case. Here we want to see if an intense flaring activity, but with low energy flares, can trigger accretion. So to do that, we developed a 3D magnetodynamical model of a classical T stars with an initial atmosphere composed by a magnetosphere, which is composed by a dipole and an octopole, chosen in order to have 1 kilogauss at the stellar surface, an initial isothermal corona of 4 million Kelvin, and a thick Keplerian, a dense Keplerian disk. The numerical setup solves the equation of conservation of mass, of momentum, of energy, and the equation of induction for the magnetic field. The model takes into account the viscosity of the disk, the gravity from the central star, the magnetic field thermal conduction, and the radiative losses from optically thin plasma. We added a Q term in the equation of energy, which is a parameterized heating function used to describe a parameterized heating release of the flares. And we developed this and we solved this module using the Pluto code. So here I will show you the results of my reference simulation. And here we have in the top view, we have an edge-on view of the system. And in the bottom view, you have the 2 poles on view of the system. And the blue region is the dense disk. And the white here is the stars. The green lines are the magnetic field lines. And the temperature is plotted in a volume rendering from yellow to red. And here it should be, okay, should start the movies. So as you can see, the flares, each flares form these hot loops and where part of the material links the star to the disk. The other part escapes from the system. And all this material produce a hot extended corona that radiates the disk. But after 24 hours, the perturbation due to flares were able to produce accretion columns onto the stars. And also the dynamic of this accretion column is highly complex and highly affected by the subsequent flares. And in fact, the flares that occurs at the base of the accretion column can disrupt the base or inject, as in this case, inject material into the accretion column. So the results of this dynamic is that the accretion column are highly inhomogeneous and density structured. So after, as you can see, after 70 hours of evolution, the time is here, the inner part of the disk is disrupted and we have several accretion columns impacting into the surface. So now I will show you the results one by one. And so the first thing is the flares generate the hot loops. Part of the material escaped from the system and we have a mass loss rate of 10 to minus 10 solar masses per year. And the other part links the star to the disk. Now all these hot loop produce what we call a hot extended corona. It's a source of UV and X-ray radiation from the disk. So another result is the density structure accretion column. Here we have a pole-on view of the system, and where there is here is represented the pressure on the material with a density greater than 10 to 10 particles per cubic centimeter. So here we have the star, and this is an accretion column. The red arrows indicate a region where a flare occurs. So now you see the effect of these flares on the base of the accretion column. So when the flare occurs, we have part of the material which is ejected out and part of the material which is injected into the accretion column. And this causes at the end a bigger accretion column, a bigger hotspot, and a denser blob that impact and affect the accretion column. So here you can see also this kind of evolution in this movie, where we plotted density surface of the stars. So this is the surface of the stars, and we plot a density map, and we can observe the evolution of the hotspots. Of course, we cannot solve with our model the shock. We do not have a stellar atmosphere, and we do not have enough spatial resolution, but still we can see where the hotspot may occur and what are the size and the shape of this hotspot. So now I should start the movie. So the first 24 hours are quite boring because we do not have any accretion columns, but then we have at high latitude two big hotspot that evolves and change in shapes. And as you can see, there are radially density structured, and sometimes they are more dense, or here less dense. So now the movie starts again. And from this hotspot, we were able to synthesize the accretion rate from the stars. And so here you have a plot of accretion rate versus time. So this is the evolution of accretion rate. And these stars here represent a sample of classical T stars present in literature. So the accretion rate of these stars. And here we have the my3 simulation. The black curve is the reference case. It does the simulation that I show you in the movies. And here you can see that there is a transient phase where the accretion rate increase. Then it reach a value which is remain more or less stable, and we enter in a regime phase where the accretion rate remain more or less constant to the entire simulation. The red curves is the same simulation as the reference case, but with a disk 5 times denser than the reference case. So as before, we have the transient phase and then the value which remain more or less stable during the evolution. And the important thing is to notice that the accretion rate of the denser disk is higher than the reference case. This indicates that the density of this disk is important for the final accretion rate onto the stars. And the green lines is the simulation with exactly as the reference case, but with the frequencies of flare, which is 4 times lower. So we have 4 times less flares than the reference case. And still with this very low activity, we are able to have accretion column in less than 50 hours and to reach a regime after 70, 80 hours. So here, the conclusion of my work. So we study the effect of this intense flaring activity on localizing close to the accretion disk. And we found that this intense flaring activity generates a hot corona that extends from the protostar to the inner part of the disk. And this also generates accretion onto the stars, and accretion may be composed by density structured accretion columns. And the accretion rates synthesized from the model are the order of 10 to minus 9, 10 to minus 10 solar masses per year. And we also synthesized the X-ray luminosity from the model. And we found that this is comparable with typical value observed in classical T-Tauri stars. And that's it. Maybe it was too fast. Can you hear me?
Yes, that was great. Thank you. Thank you. Are there any questions? Okay, we have one here from Tom Begues.
Okay.
There may have been a part of earlier that I missed, so maybe this is a simple question, but what is sort of, for your disks and the way you set it up, what would be sort of the accretion rate that it would have without any of the flaring activity? And if that is zero, why, why wouldn't you expect some accretion? In other words, sort of, is there some element of the model that's lacking, sort of a viscosity or flow of material inward in the disk?
Sorry, I missed half of the question. Can you please repeat? May I skip on? Oh no, sorry. Can you repeat again, because I skipped half of the, I missed half of the question.
Okay, sorry. Yeah, we're having issues over here hearing. So in your models, it seemed like basically there was no accretion before the flares, right? So you had sort of like a steady state.
Yeah, we started.
Maybe that's wrong. If there was a steady state in the sense there was basically no material floating from flowing from the disk onto the central star.
Yeah.
Normally, you would expect in sort of a magnetospheric accretion that there would be material flowing directly onto the star due to the flows of gas in the disk. What's missing in your model that this isn't represented, or am I misunderstanding your?
We started from an idealized case, so no accretion on the disk, and so we started from this situation. So just stars surrounded by a disk which is in equilibrium. And we wanted to observe only the effect of the flares. So for that reason, we decided to start without any accretion from other sources, like, for example, viscosity. If you let this kind of system evolve without any flares, you will observe still the accretion columns due to viscosity. For example, there are another paper from Romanova that produced that let this system evolve for several stellar stellar period, and they found accretion columns. But we didn't want to mix up all the effects, so we started with the simplest possible case. So no accretion column, and then all the accretion columns that we have we know that they are due to the effect of the flares. That's why we started without accretion column. I don't know if I would answer to your question.
Yep. Okay. Thank you.
Okay. Perfect.
We have a few more questions here, but I'm afraid we will have to move on to the next talk. Before we thank you again for your talk, I will say that we should continue the discussion on the chat on the YouTube page. So maybe you can also have a look there. So thanks again for your talk.
You're welcome.
Yeah, that was Salvatore Colombo. And now our next speaker is Fabio Reale. And I will try to switch over to him.
Hi.
Just need to clean up just a second, our broadcast here. If you could already share your screen.
Hi. Share?
Yes, we still need your screen. If you can share your screen.
Okay.
So if you click on share screen.
Yes, I did. Let's share. Okay, yes.
All right, yeah, so something is coming in. Okay, and then you can go to your presentation full screen.
Oops.
And
sorry.
You can go to the beginning.
Okay, can you hear me?
You can go to
Thank you for
full screen, and then you can actually click on hide. Yeah, exactly. At the bottom to excellent. Oh yeah, now you need to go to full screen.
Okay, thank
Perfect.
you for
Okay.
letting me talk in this very interesting meeting. And so I will talk about oscillations in X-ray flares observed in the Orion region. And I thank Salvatore for his nice introduction, which will allow me to go very fast about the scenario. This is the picture that we have about protostars. Many of them have still circumstellar disks with accretion flowing along magnetic channels, and but this is only a picture. So now our question is: do these magnetic channels really exist? Is there any strong evidence for these magnetic channels? And I will show you that flares, X-ray flares, can be probes to show this. So let's focus on the Orion COOP, the 2 weeks observation that allowed to observe many flares. And this is a typical light curve of flare that show that typically these flares are very long, about 1 day long, and very hot, typically well above 100 million degrees. And this is very important. And several of them have been shown to have been proved to show pulsations in their light curves. And in this study by Lopez Santiago, it was they were detected with sophisticated wavelet analysis. And here we will focus on a specific case, which is very well observed, a flare observed on D772, which is a star with a disk. This is the light curve as it appears in the paper, in the general paper by Favata et al. 2005. And the wavelet analysis by Lopez Santiago shows that there is a very strong periodic signal in the initial phases of the flare, and this periodic pulsation shows up very clearly when we apply a boxcar to the light curve, and these are called quasi-periodic pulsations that modulate the light curve. And the interesting thing is that the period is about 3 hours, while the flare duration is about 20 hours. So quasi-periodic pulsations are observed also on many other stars, for instance, on M stars, being detected on M stars. And now to investigate the origin of these pulsations, I will start from the solar corona, which is the only template we have of a resolved corona. And the bright corona is made up of closed coronal loops, as you all know, which are of magnetic origin. And the plasma is confined inside these magnetic channels, closed magnetic channels. And it is believed that many flares are due to the impulsive energy released due to, for instance, impulsive magnetic reconnection. So now I will address the flares that occur in a single magnetic loop, magnetic channel. And in this case, we can model the flares as occurring as if the magnetic channel confines the plasma, and the plasma moves and transports energy only along the magnetic field line. In this case, we can describe the plasma with hydrodynamics, with pure hydrodynamics, without any role of the magnetic field, and with only one coordinate, which is the coordinate along the loop. So we solve numerically these are the hydrodynamic equations of mass, momentum, and energy conservation, which are very similar to those shown by Salvatore, but except for the absence of any role of the magnetic field. And we act on the energy equation by including an empirical heating pulse in the energy equation. And here in this model, the two main basic parameters are the loop length and the parameters of the heat pulse, of course. If we include a heat pulse in the energy equation, we generally obtain a flare-like evolution. this means a very fast rise and a slower decay due to plasma cooling. And what has been found recently, about a couple of years ago, is that if the heat path is quite long, the light curve is smooth, but if it is very short in time, the light curve results to be modulated by pulses, by periodic pulses, which is similar to what we observed in the B772 flare. And the physical reason for this is that if the flare, the heat pulse is short, the pressure has no time to reach an equilibrium inside the loop, and this creates a depression which triggers pressure waves moving back and forth, sloshing back and forth along the magnetic channels, which doesn't occur if the heat pulse is sufficiently long to have pressure equilibrium, which is on the right hand side the map, pressure map. So there is a condition for which the pulsations are or are not triggered, which is that the pulse duration must be obviously shorter than the sound crossing time along the magnetic channel. And if we apply this condition, and if we consider the sound crossing time along with a period of about 3 hours, which is the period that we observed in this flare, we obtain a possible length of the magnetic tube, which is very huge. It's about 20 solar radii. And also the condition to trigger the pulsations is that the heat pulse must be shorter than about 2.5 hours. And in fact, if we consider a numerical simulations with a heat pulse that is longer than 3 hours, we obtain quite a smooth light curve, which doesn't match the observed one. But if we apply a shorter heat pulse, which is about 1 hour long, we obtain a pressure map that is very clearly, which shows very clearly this zigzag evolution, which is evidence for the presence of the pressure waves. And if we derive the light curve, then we have a very clear match with the observed light curve. And so if we compare the short and the long heat pulse, we see that clearly. If we consider a short heat pulse, we have an improvement to fit the light curve. So essentially, this is the end of my presentation. And if we have such a long 20 solar radii magnetic channel, it is long enough to connect the star to the presumable disk that is still accreting onto the star. So this might be a very clear and strong evidence of the presence of such magnetic channels that connect the star to the disk. And this movie shows what we would really observe. This is not a cartoon. This is the real bright intensity that we derive from the model. So in conclusion, the coherent pulsations that we detect in flare light curves of the Orion protostar is a clear evidence for single flaring loops. And if this is so, their long duration and the long periods are all evidence that these magnetic channels are really very long, so long as to connect the channels with to connect the star to the disk. Okay, so that's all. Thank you.
Excellent. Thank you. Okay, I switch back to this view here. Yeah, thanks for your talk. I'll see if there are questions coming in. I'll maybe start with one question. Do you actually think that by adding more simultaneous observations at other wavelengths, you would be able to put more constraints on the underlying mechanism? Would that be of any help?
Sure. Hard X-ray observations will be very valuable, but also probably radio, and I would say white light. If we can detect flares in white light, that might be also useful because we would see what happens at the foot points of the channels.
Yeah, that would be interesting. Are there other questions? Is anything coming in online? Okay. Yeah, we can always continue the discussion online. So let's thank Fabio again for this second very nice high energy look at the details of Orion. Thank you.
Thank you.
Okay, and we will switch to our next speaker, with Wafa Zakri. Just switch over here. Hi, Wafa.
Hi.
Excellent. So we are basically ready to go. So if you could share your screen, then we can put it into the
I shared my screen. I tried to choose entire screen. Didn't share.
Yeah, I don't see it at the moment actually. So if you could try again, clicking on share screen.
I shared the screen. Trying to click to entire screen, it didn't share the screen. I don't know why. Oh my gosh.
So what happens if you click on share screen at the bottom of this?
It looks like freezing. I can move between your entire screen, application and window, Chrome tab, but cannot choose share.
So if that's the case, then maybe what we would have to do is to switch to the next speaker, and then you maybe need to restart.
I can disconnect the link because I tried this 5 minutes ago. It was working.
So our problem is that we don't see your screen share here.
Can I reconnect the link?
Yes, sure. Yeah, let's try reconnecting.
Okay.
Okay, so we. Okay, so we wait briefly for Wafa to come back. Hello?
Hello? It didn't share the screen. I don't know why.
So now you're actually on the call twice. So you didn't really leave the previous call. So
you can move to the next speaker. I will see the problem. I don't know why. I tested about 5 minutes ago. It was working.
Yeah, so the problem really is that we see you, but we do not see your screen at the moment. Do you want to give it one last try, and then we will otherwise switch over to the next speaker, and then you can totally reconnect in the meantime, and then we'll have your talk after that. after
Sure.
Adam's.
Okay. Okay.
So nothing is happening if you share the screen. Okay, I think we will have to move on to the next speaker for the moment, and then we'll come back to Wafa after Adam's talk. So, but I don't want to totally surprise Adam with that, so I will switch over to say hi to Adam. Hi, Adam. Are you okay giving your talk now? I'm not sure the audio is fully working.
Test. Any audio?
Oh yeah. Now okay. Now it works. Excellent. Yeah, and I see your screen, so I'll add you to the live stream. So Adam is joining us from Florida on SALT and Orion, and so yeah, Adam, please go ahead.
Okay, good. So I'll be telling you about SALT around Orion Source Eye. And I want to first highlight that if you want to see any of these slides, they are all accessible on the web at that URL at the bottom of the screen there. So yeah, and I don't know if you can do this, but maybe paste that somewhere in the program or something along those lines. And that might be relevant because there are a bunch of hyperlinks throughout the talk. So the illustration in the background here is an artist's impression of Orion Source Eye, which is a disk around a high mass protostar. And I'll tell you a little bit more about it. But you can see there's an outflow coming out, and that little blue haze in the center is the part that I'll be focusing on. So if you want to see the papers or access any of the data, the fully processed data, those are all available online. So again, these are all hyperlinks. You can grab the data, the paper on that you may have heard referred to in the first talk of this conference by Tomoyo Hirota. And then the SALT paper, which I'll be focusing on a little bit more. So I'm going to breeze through the introductory material because I can just refer you back to the first talk of today. So you heard, if you look at that first talk, you heard that Orion, the Orion explosive outflow is what we're picturing here. So this is molecular hydrogen and iron shooting out from central region where Orion Source Eye lives. And that central region is also blowing out a lot of carbon monoxide. So that red haze that's shown there is CO as seen by ALMA. And the hypothesis is that this outflow was likely driven by the dynamical decay of a multiple system that happened around 500 years ago. And that's because we see all these back in a common, we can trace the proper motions back to a common location marked by the yellow X. Just very briefly, you might have also seen Sergio Zib's talk about proper motion measurement. And I just want to highlight that the proper motion measurements do point back to a common origin. And there have been some more recent measurements of this source X in the near infrared that show that that might be the third partner as opposed to radio source N. So there's a lot of discussion you can have about what happened in Orion 500 years ago. But I'm not going to talk about that here because I want to keep this brief and focused on SALT. So the data set that I'm going to be talking about is similar to what, again, was talked about in the first talk at the very high resolution ALMA observation of Orion. And we're just going to be looking at that very central source, Orion Source Eye. But I'll just show that, there are around 60 other point sources in the field of view. And so there are a lot of protostars in this region that we haven't written anything about. So Orion Source Eye when you look at it at very high resolution, so now this is 0.04 arcsecond resolution approximately, you see an extended disk. And so this is ALMA band 3. If you look at ALMA band 6, so at 1 millimeter, you get higher resolution, and ALMA band 7, 850 micron, even higher resolution. It's a really clearly edge-on disk, fairly boxy, with a little bit of asymmetry in the center. And with these images that I just breezed through are continuum images, but if you look in different spectral lines, you start to see the outflow. And again, refer back to the first two talks of today. This is now showing a water line on the top and bottom of the disk, where the red contour is showing the continuum. And so the way we inferred the mass of the disk is by looking at the Keplerian rotation curve, particularly of that water line, because it has it was detected at the most different radii from the central source. So this is now the position velocity diagram showing the fitted curves, and the red curve there is the 15 solar mass curve that we fitted to this. But that's really all background. What I want to tell you that's fairly new is what we found in the center here. So now this blue hazy image is an image of a line of NaCl salts. And I'm going to tell you more about where that came from. But just to emphasize that when I'm talking about salt, I really am talking about table salts. This is a picture of salt sitting on my table. And we also detected KCl. There are various transitions of salt spread throughout the ALMA bands we observed. And so I'm going to show you a few different spectra highlighting these individual transitions and showing that this is really a very definitive identification. There's no question that what we found is salt. We've also found different isotopologues of salt. So in this slide and the next few, the red vertical dashed lines highlight salt NaCl emission lines. The blue highlight KCl emission lines, and they're all identified by their different vibrational and rotational quantum numbers. And all you're supposed to take away from this is that there are quite a lot of these transitions. And this is band 3, moving into band 6, several more. There are lots. And the pattern is just very clearly picked out. So there's no alternative explanation for it, the lines at least. That much is clear. Okay, done showing you spectral, just spectra. Those are interesting enough, but that's just what we use for the identification. And now I want to show you a little bit about the morphology of the line. So where is the salt emission coming from? And I'm going to step through the 3 different ALMA bands we observed. So we took observations in ALMA's band 3, 6, and 7. So 3 millimeter, 1 millimeter, and 850 microns. So in this plot, the red contour is the 1 millimeter continuum, and the white contour in the grayscale is the band 3, so the 3 millimeter line of salt in the 3rd vibrationally excited state, and it's the rotational transition J equals 7 to 6. And you can see the resolution is fairly coarse here, but you have these 2 lobes tracing the outer edges of the disk. If you go to 1 millimeter, you start seeing a few different interesting features. First, it's higher resolution, of course, but also you're starting to see that the inner disk is really clearly missed, and we're tracing just the outskirts. And then finally, at the highest frequency, this is now band 7, so 850 microns. We have very high resolution, and we're seeing that the salt is really on the top and bottom of the disk. It's tracing the upper and lower surface layers. And this is in large part because of the opacity of the disk itself. Those inner contours are at a few hundred Kelvin brightness in the continuum, which implies that that disk is optically thick in the center. So it's not necessarily that there's no salt emission coming from the center, but it may just be that it's absorbed by the optically thick dust disk. Now, again, relating to the earlier talks about SIO, we can compare the morphology of the salt and various SIO lines. So in this plot, the red contours are one of our higher signal to noise salt lines. And again, it highlights the upper and lower layers of the disk. The background, the grayscale, is showing the V equals 0, so the vibrational ground state transition of SIO 8 to 7. So highly excited rotational state of SIO tracing the outflow. And you can just see that it's this V-shaped thing coming off the entire disk. And that's what you saw in the first talk that really shows this is a disk wind type. The outflow is coming from the whole disk. But the higher excitation lines of SIO, something like the SIO B equals 5, J equals 8 to 7 line shown in blue contours, traces the inner disk even further in than the salt. And just to, you should ignore the contours in the top left. This is another view of the same thing. I'm going to skip over it. So one of the reasons we should care about seeing these salt lines tracing the surface layers of the disk is that this is a way we can measure the mass of the central source. So this is a position velocity diagram where on the left side is a model and on the right side is the data. And of course, the model is a filled disk. It has emission coming from all positions, whereas the data, we have some absorption from the continuum, but we can use this to directly measure the dynamical mass of the central star. And we can do this in Orion. So the question comes, can we do this in other sources? Can we use the same sort of dynamical mass measurement? And the answer is already yes. We have detected salt in at least one other high mass young stellar object. So Luc Maud published a paper earlier this year that I hope it briefly mentioned this salt detection, but I don't believe showed this plot. We have another work in progress on that. But in short, these salt lines are detected. They're double peaked if you average over the source. So we do believe we can use these salts to measure the dynamical mass of other stars, other high mass protostars. So you can then ask the question, why are we seeing salt at all? Why are we seeing salt in protostar? Because previously they've only been seen in AGB star atmospheres. In this case, in AGB stars, that's associated with dust formation. In this case, it's most likely that the salt is coming from dust destruction as the dust is being raised into the outflow. We also are seeing higher excitation lines here than have ever been detected before in AGB stars. So it's not quite similar in that respect. So we can ask, is this just very hot gas at high temperature? And the answer is unclear. This is a rotational diagram where the black and cyan lines, the rather flat ones, show the vibrational temperature, which means we're measuring the ratio of level populations in rotational states at the same vibrational state. Wait, I said that backwards. This is different vibrational states at the same rotational state. So the vibrational temperature is very high, whereas the green and blue lines are showing that the rotational temperatures are fairly low. So we have a discrepancy between the vibrational and rotational temperatures. We see this in both NaCl and in KCl. So I don't have a good model to explain these temperatures yet, just have a few ideas. One way to do this is with a strong non-black body radiation field in the mid-infrared. And it's unlikely, but it's possible that could be produced by certain types of dust grains. Another possibility is that UV or optical excitation is doing this, but that may dissociate the molecules rather than excite them. So the non-black body emission model, here's a very contrived view of this. You take the top panel shows the input radiation field you use, where you just put this wide line at a particular wavelength that is completely not physically justified, and you can reproduce the rotational energy diagrams that I was showing before, as shown in the bottom panel. So the bottom panel is showing all of the different rotational states and vibrational states, where the red and the black dots are the ones we observe. And you can get these two different temperatures, maybe, in that case. A perhaps more physically motivated one is this electronic excitation approach. And so this is a plot of the rotational diagram of molecular hydrogen toward the Orion Nebula, showing what happens if you have electronic excitation. So you have photons being absorbed by molecular hydrogen, it excites them to a higher electronic state. Then when it decays from that excited electronic state back to the ground electronic state, it can change its vibrational and rotational quantum numbers. But those changes are governed by selection effects, which can result in basically taking a cold rotational diagram or whatever temperature you have in your rotational diagram and copying them to different vibrational states. But I don't yet know if this is actually possible for salt. It's just the physical mechanism is plausible. I'll skip over this slide very briefly. Just shows you that these lines have these molecules have transitions at low frequencies as well in the BLA range. And so I'm going to leave you with this final slide, highlighting some possible future uses for these lines, where the primary likely uses are using them to measure kinematics of disks around high mass stars to measure the mass of the central protostar, and possibly, depending on the mechanism, to probe the radiation environment around high mass young stellar objects. So I've gone a little bit long here. I'm ready for questions. Thanks.
Excellent, thank you. Okay, yeah, we see if there are questions coming in. There's a question by Paula Tejera. Can you get a dynamical mass from the water lines? And if so, how does it compare to that from the salt lines?
Yes, so can you hear me? Yes, you can hear me. You can hear my echo. Should I not have unmuted myself? Sorry, okay. Yes, in the 2018 paper, we measured dynamical masses using both water and salt and compared them. And you can see all those measurements at the end of the paper. They're similar. With salt, we got something like 13 to 14 solar masses, and with water, we got around 15 using two different methods.
Okay, cool. I also have one question. And are you aware actually of any NaCl non-detections toward other objects? So is it possible to even directly compare this to conditions in other objects already, or is this completely unique at this time?
Yeah, I mean, non-detections are the default, but that's a sensitivity and resolution issue. If you notice, I don't know if I pointed out the scale bars here, but the Orion Source-Side disk has a total extent of 100 AU. And to really get enough signal to know, like, you don't see this in the, say, like 0.1 to 0.2 arc-second resolution data of this source. You barely see these lines at all. It really was the high resolution and high sensitivity together that allowed us to detect them. So, for example, in W51, there are several high mass young stellar objects where we do not see the salt lines, but it's entirely consistent with, you could put hide Orion in our beam and you would not see them. So this is really a new field in the sense that we need very deep, high resolution data to look for these, and that's coming, right? People have not done very much ALMA very long baseline observations of high mass young stellar objects yet. So there may be detections or interesting non-detections forthcoming.
Yeah, very cool. Thanks. Are there any more questions? We have one more question from Alvaro here.
Hi, Adam. Really cool result. I'm curious because your observations suggest that this is a really nice tracer, perhaps also for the mass. Although it's opaque and can walk around, but do we know the abundance of these molecules good enough that we can use it as tracer of the mass, for instance? That would be super cool.
Yeah, so we have no clue about the abundance, and in large part that's because the way you would measure abundance is you compare the total column of, say, of the NaCl line to some reference, H2, dust, whatever. The problem is we don't, like, the dust at the same location as the salt emission is partly optically thick, and we don't really know how much material there is there. And the H2, well, I'd be very suspicious of any dust to gas ratio you measured here. We really know very little about the composition of this particular part of the disk. So I would not hazard even an order of magnitude or 5 order of magnitude guess about the abundance yet. It would be great to know though.
Cool. Yeah, thank you. Yeah, thanks again for your talk, Adam. Excellent. And in the meantime, Wafa has patiently recovered the screen share, so we can have her talk now, and I will begin to switch over. Let's see, there she is. And we directly have the screen. So that's all set up, Wafa. That's great. Thanks for recovering, and thanks for your flexibility and just shifting your talk a little bit. So it's all yours now, searching for outbursts in the Orion molecular clouds.
Okay. Hello, everyone. Are you hearing me clearly? Hello, everyone. First, I would like to thank everyone who gave me the opportunity to be here today. The talk I would give today is talking about the outburst of young stellar objects in the Orion molecular clouds. So in this talk, I would focus on 2 big points. The first one is about the fraction of material accreted during the burst. The second one is about the difference between pre-main sequence and protostellar burst. So both of these points are required to measure the rate of the burst. So here, if we want to know the fraction of the mass accreted during the burst, by assuming the fraction can be determined as if we know the rate of the burst time of the burst, and ratio of the mass accretion rate. Here, there are two examples of protostellar burst. The first one is flat spectrum protostars Hubs 223. The lower one is Hubs 383. So the upper one, Hubs 223, is considered to be a FURI outburst that detected by Will Fisher. So at the left image, we can see the source before the burst. At the right, the source after the burst. So these images detected in 3.6 micron, the left one by Spitzer in 2004, the right one by Wise in 2010. So the burst occurred between this time interval by increasing in about by a factor of 5 in flux density. So at the left, we can see the SED for the source, where the red is the source before the burst, blue after the burst, and green is IRS immediately after the burst. The lower example for class 0 outburst Hubs 383, where the image is showing the burst time between 2004 and 2018 increasing by a factor or by 30 times larger in flux density, as we can see in its SED. So this detected in MIBS 24 micron in both epochs. Here, by using the same data set that Will Fisher used to detect the protostars, we used the same data set of Spitzer 2004 and Wise 2010 by taking the difference in one magnitude versus the other magnitude. So we taking the difference between 3.6 and 4.5 in both epochs, Spitzer 2004 and Wise 2017. 2010. From that, we only found one outburst out of 2088 sample. So if we can see the images, the lower one is before the burst, the upper one is after the burst, showing increasing in 4.5 micron detection, that is about 1.6 magnitude. So based on this finding, we estimate the rate of accretion outburst for young stars with a disk, and compare with the burst rate of protostars that done previously by Will Fisher. So the plot is showing the probability of the burst versus the time interval between the burst, and from the comparison, we found one burst in protostars every 1,000 year and one young star with disk every 12,000 year, which is about 10 times higher variation in protostar. Here also, by having a new photometry from new Spitzer Orion TFE, the final epoch survey in 2016-2017, where Spitzer remapped the entire 2004 Spitzer Orion field at 3.6 and 4.5 micron, and now we are able to study the variation of the pre-mate sequence and protostars over about 13 years interval. Here, our detected of class 0 outburst, Hubs 12 and Hubs 124. We have two sets of images. The left one is for Hubs 12 and the right set is for Hubs 124, where the upper images detected by Spitzer by IRAC1 3.6 magnitude, the lower one detected in the second band 4.5 micron. So we have three different epochs observation of Hubs 12, while we only have two epochs of Hubs 124. So it's clearly showing that for Hubs 12, the burst occurred between 2004 and 2009 and keep bursting until 2017 in both bands of observation, while in Hubs 124, we only have two epochs showing that the source looks like growing in magnitude over 13 years. Also, these sources are detected in 70 micron. In this plot, we have a detection of all sources of all detected outbursts in MIPS 70 micron 2004 versus PAX 70 micron in 2011. So the solid line show that MIPS and PAX are equal. The dashed first and second line showing that PAX is 2 times and 3 times higher than the MIPS. And we can see clearly HABS 12, HABS 223, and HABS 124 in the right plot that they have increasing between 2 to 3 times in PAX than the MIPS. Here in the histogram of both protostar upper histogram and pre-main sequence star with disk, the lower histogram, we're trying to detect the variation in 1 magnitude for protostars and pre-main sequence, where we have the number of bursts and fades versus the magnitude change over 13 years, so the difference of time between 2004 and 2017. So we see here in the protostar, the number of bursts and fades are equal from the sample of 390, and while the star with disk giving lower number of bursts than the fades out of 2987 sample, we only found like less bursts than the fades. Here we have the probability distribution of 1 magnitude change and 1.5 magnitude change of the previous data, looking for the burst rate of both magnitude threshold. So for the 1 and 1 magnitude change, the ratio of protostar to class 1 is approximately 1 every 1,000 year versus 12 in 1.5 magnitude change, while in 1 magnitude change, there is 1 burst every 233 versus 1800 years. So we can see here, that the estimate time interval of the bursts are 10 times larger rate for protostar than pre-main sequence stars with disk. So if we go down to get to 1.5 magnitude to 1 magnitude change, the rate of the burst increases, but the difference between protostars and disks stay approximately the same. So in the summary, this is our result we found from using. So this is the result of burst rate using Y-Spitzer data and Spitzer data. All give that the rate of the burst of long term of higher than 1 magnitude variability that gives the protostars about 10 times higher variation than the disks. The second result is the detection of 3 new outbursts with about 2 magnitude variation over 13 years. So the first outburst is the previously known HABS 223. The second, the other two are our result for new class 0 outburst, HABS 12 and HABS 124. Thank you.
All right. Thank you. Yeah, very nice talk. Thank you. Excellent timing also. That's perfect. There's already one question that came in online by Paula Tejera. I'll just read it out to you. You also see it on screen. HOBS 12 and HOBS 124 have a nearby source. What is the physical separation, and could these be wide binaries?
Can you repeat the question again? I'm sorry. They asked about the companion of the source?
Yes, about HOBS 12 and HOBS 124. You may not know out of the top of your head, but these two sources, Paula is saying that these two sources have a nearby source, and she's wondering what is the physical separation, and could these be wide binaries?
Yes, actually, if you can see the light curves that I did here to know the first time, we have like HABS 12 with its companion. They are very close to each other and cannot separate by wires. So we did like a combined observation for that, but we can separate that by Ys. So for hubs 12, I'm sorry, I didn't show that the left one is the companion and the right is hubs 12. While for hubs 124, the upper one is hubs 124 and the lower than this is hubs 125. Is it the question about what's the companion or why they are separate? Can you?
Yeah, I only have this question as it came in online, so I would suggest that you continue the discussion in the Q&A and in the chat.
I don't know. Yeah, I don't know
window.
if they asked about the name of the companion or why they are closed.
Yeah, yes.
They are
You
not
can.
closed.
Yeah, you
Okay.
can continue the discussion in the chat window. Yeah,
Okay.
excellent. Cool. Is there anything else? Other questions? Do we have a local question? Yeah, or we have a local question here by. Just a second.
Yes, so a very quick question, but do these observations also allow you to constrain the duration of these outbursts? Do they allow you to test if they vary between class 0, class 1, and class 2 objects?
Do you mean if we can do study the rate with more than 1 magnitude change or lower than 1 magnitude change?
I mean, mostly the actual time of the outburst. Like, does it last 1,000 years in class 1 and 100 years in class 2, or the other way around?
Oh, how long it lasts? Are you asking for how long it lasts?
Yes.
Yes.
In our results, I think I don't have exact time for the burst, but the burst occurred in short duration, but I don't know how long it lasts.
Okay. Yeah, thanks. Cool. Yeah, if there are no more questions, thanks again to Wafa for her very nice talk. And that concludes this session. We'll now go into hypercaffeination here in Leiden and then start our fourth session soon. So we will then switch to a different link, and which is already on the website. And so see you soon for the continuation. Thanks. And let's thank all the speakers of this session for an excellent set of talks once more.